The James Webb Space Telescope provides the infrared sensitivity to observe the earliest cosmic structures, capturing galaxies forming immediately after the Big Bang. Observations by Lebey et al. Have targeted a specific epoch at a redshift of z=10. In the standard cosmological timeline, this period occurs roughly 600 million years after the Big Bang. These observations identified mature stellar masses reaching 10 billion solar masses already in existence during this early stage of cosmic history. Plotting cosmic time against stellar mass reveals the Lebey findings: 10 billion solar masses at 600 million years. The standard model defines a strict maximum for mass accumulation here. The observed galaxies sit impossibly above this theoretical ceiling. Star formation efficiency measures the percentage of halo gas that converts into stars. To reach 10 billion solar masses by redshift 10, this efficiency must exceed 100%, requiring a halo to convert more gas into stars than it actually contains. Resolving this discrepancy requires addressing potential systematic errors in spectral calibration or evaluating gaps in our theoretical understanding of early universe gravity. We can resolve this tension by questioning the assumption that the MOND acceleration scale, A0, is a universal constant. Mode identity theory proposes that this scale evolves alongside the expanding universe. The observational data suggests that gravitational boundaries function differently in the early universe. These formations become predictable when we account for the evolution of the cosmological framework. Since 1983, modified gravity models have treated A0 as a rigid acceleration threshold, fixed at 1.2 × 10⁻⁻10 meters per second squared. Below this value, gravitational effects deviate from Newtonian predictions. For 40 years, astrophysics has noted a specific alignment. A0 is nearly identical to the speed of light multiplied by the Hubble constant. Mode identity theory explains this relationship through topological geometry, defining these values as specific positions on a cosmic standing wave. This diagram shows the Hubble horizon as a topological well. In this framework, both A0 and the Hubble constant occupy the same n=1 edge mode. Both are tethered to the same expanding horizon. Because they sample the same edge, their ratio is mathematically fixed. The predicted ratio of 0.184 matches the observed value of 0.183. The density of this horizon is proportional to the inverse square of the Hubble expansion rate, which ensures the stability of this ratio across different eras. This coupling implies that A0 cannot be a constant. As the Hubble horizon expands over time, the acceleration scale must evolve in tandem with the age of the universe. Traditional models overlook this expansion. They assume the acceleration limits governing early galaxies were identical to the limits we measure in the local universe. The MIT scaling relation defines A0 at any redshift as the local value multiplied by the ratio of the historical Hubble expansion rate to the rate we measure today. By maintaining A0 as a constant, standard models effectively ignore the mechanical expansion of the universe when setting the limits of gravitational binding. We can now calculate the exact value of A0 at the redshift 10 epoch targeted by James Webb. This calculation uses standard parameters: a matter density of 0.3 and a vacuum energy density of 0.7. This is the Hubble evolution equation, which determines the rate of cosmic expansion at different stages of the universe's history. Substituting a redshift of 10 into the volume expansion component gives us a factor of 1331. Multiplying by our matter density and adding the vacuum energy results in an internal value of approximately 400. The square root of 400 reveals the expansion ratio. At redshift 10, the universe was expanding 20 times faster than it is today. We apply this multiplier to our scaling law, increasing the local acceleration scale by a factor of 20. This results in a physical acceleration scale of 2.4 × 10⁻⁹ meters per second squared for the redshift 10 epoch. Determining the raw threshold is only the first step. We must calculate how this higher threshold changes the actual force of gravity. In the deep-MOND regime, the effective gravitational acceleration is proportional to the square root of Newtonian gravity multiplied by the A0 threshold. When we insert our 20 times multiplier for A0 under the radical, the result is a 4.5 times increase in effective gravity. At redshift 10, background gravitational binding is roughly 4.5 times stronger than standard models predict. This defines the rate of early cosmic structure formation. This stronger gravitational environment directly impacts the collapse dynamics of the galaxies observed by James Webb. The time required for a structure to collapse, the free-fall timescale, is inversely proportional to the square root of the gravitational acceleration. As the effective gravity increases by a factor of 4.5, the time required for matter to fall together decreases. The 4.5 times increase in gravity results in structures collapsing roughly 2.1 times faster than previously estimated. This faster collapse resolves the star formation paradox identified in the Libet data. Because galaxies collapse twice as fast, they accumulate 10 billion solar masses in half the time. The theoretical limit for stellar mass moves upward. The required star formation efficiency drops from an impossible 100% to a permitted range. These galaxies are baryonic formations, naturally following the mechanics of a stronger gravitational epoch. Mode identity theory introduces a structural inversion of the assumptions used in standard modified gravity. Modern cosmology usually treats the acceleration scale as a constant, while allowing the cosmological constant, lambda, to potentially evolve over time. The dimensional hierarchy of MIT requires the opposite. In this framework, A0 is an edge mode that must evolve with the Hubble horizon. Lambda is a surface mode, which remains permanently fixed at all scales. This theory mandates that lambda is perfectly constant across all cosmic epochs, with no exceptions. MIT provides clear, falsifiable criteria that distinguish it from standard models. The theory is falsified if galaxy rotation curves at high redshifts show the same acceleration limits we see today. It is also falsified if distant supernovae reveal a changing cosmological constant. Data from the James Webb Space Telescope suggests that assuming a static acceleration scale has obscured the role of kinematic evolution. We are now integrating horizon physics into our model of gravitational limits.